My name is David Calhas. Today I'll be presenting computing a human-like reaction time metric for stable recurrent vision models. This is a paper that was presented at NeurIPS in 2023. So in this presentation I'll be going through first what is recurrent backpropagation. These are two papers, so the original one and one that is reviving recurrent backpropagation by Liao. Then stable and expressive recurrent CNNs, and finally the computing a human-like metric. So I've divided this presentation like this because computing a human-like metric paper has multiple methods that come from previous studies, and I think it's important to understand those ones first. So let's consider an input x and a set of weights w. If we perform the dot product of x with w, we'll arrive to a hidden state h. And what happens in backpropagation is that we compare our hidden state with the target variable and compute a cost function L. When we are performing backpropagation, we take the derivative of L with respect to the parameters. For instance, if we want to optimize W, we take the derivative of L with respect to W. And if we want to optimize previous layers that go earlier than x, we take the derivative of L with respect to x and continue propagating, taking the chain rule. Now, what happens when we have feedback loops or recurrent layers? So consider the same case. We have x, we do the dot product with w, we forward to h, and then we have this loop parameterized by u. So we can have an arbitrary number of iterations that repeat the dot product of h with u. And what happens is we are doing the same thing. We optimize our parameters using the cost function L, comparing with the ground truth y. But to do this, we have to unroll our graph and save all of the intermediate states h in order to perform the chain rule and optimize all of our parameters. Now, this method is expensive because we have to store all of these intermediate states h, and the final part, when you, for instance, if you want to optimize u, the gradient is going to be the sum of all of those intermediate time steps. Now, these are some disadvantages. So we have to store all of those states, so there is memory consumption issues. For energy-based models, which is something I'm really interested in, they take a lot of iterations to converge sometimes, and storing all of those states is not feasible. It also, backpropagation through time does not handle well too many iterations, since it occupies too much memory, and the models may not converge at training time, because if we do not do all of the iterations because we don't have a GPU that fits this computation, we may not have the necessary iterations to correctly optimize our model. Furthermore, it accumulates numerical errors because you can have the effect of vanishing gradients or exploding gradients depending on how your function behaves. And all of these makes this algorithm impractical for long sequences when dealing with RNNs. Now, in 1987, Pineda and Almeida, and something really interesting, Luis Almeida was a professor here in Técnico. They proposed a rolled version of the backpropagation algorithm. So consider a function f that takes as input ht and is parameterized by u. We say that this function outputs the dot product of ht with u, and consider that repeating this function will make the model reach a steady state h star. In the original paper, they defined this function psi that receives h and w and computes the difference between h and the function f receiving h. And they say that when this function is 0, we arrived at a fixed point, right? Because if my present state is equal to the next state, then we are at a fixed point. And so they take the derivative of this function with respect to u, And they do all of these computations, which frankly you do not need to know, but by equaling these to 0, they arrive to this closed form solution right here, which says that the derivative of h star with respect to u is going to be the identity minus the Jacobian of f with respect to h star, inverse of that, times derivative of f with respect to u. Now, this is a really cool solution. However, taking the inverse of these may be very costly. And what the authors back in 1987, independently by the way, they arrived at this solution of the algorithm independently. They define an auxiliary variable z and multiply the term I minus Jacobian of f h star on the left part of both sides of the equation, and this one cuts out and it ends up in this formula. Now with this they can do fixed point iteration because we have z on both sides of the equation. They initialize z with some number. In their case they say that it can be the derivative of the cos function with respect to h star, and perform fixed point iteration with this. In the original algorithm they say that they stop when the z is less than a certain threshold to the previous z. So in other words, that the series converges. So more recently, Liao, in the paper Reviving Recurrent Backpropagation, they proposed multiple ways of doing recurrent backpropagation besides the original one. And the most used and most important one is the one related to the Newman series. So they have this series, which is basically a sum of the powers of the matrix. And conveniently, this series has the following solution. So it's identity minus A, taking the inverse of that. Now, this is really convenient because this formula right here, if we replace A with the Jacobian of f with respect to h star times z, this is exactly what we have here, right? So they plug this in and they propose a new fixed point iteration where these two equations rule that fixed point iteration. And they say that as long as the Newman series converges, the algorithm or the model during training will converge. You can think of this as an estimation of the true gradient, because they don't take infinite components of this series, of course. They only go to k steps, and they say that you don't need to perform a lot of steps for it to converge. So how does this impact the original diagram? So we still have our input x, we multiply it with w, get our hidden state, and then we are going to perform fixed point iteration, which basically we repeat the dot product with u until we reach a steady state. Let's say that our steady state is ht. Compare it with our ground truth, take the cost function, and we are going to perform fixed point iteration using the last two hidden states. We repeat these k steps, and then instead of propagating through all of the hidden states that were intermediate, we propagate directly to the input. So there is no need to save the intermediate states that were previously saved using backpropagation through time, which means that our algorithm is constant in memory. Now, I have this really cool XKCD meme, which basically there are two guys, one of them is looking at the other, and this other guy is looking at a blackboard full of mathematical formulas, and the guy that is looking at him says, "Amazing, watching a physicist at work exploring universes in a symphony of numbers. If only I had studied math. I could appreciate the beauty on display here." And the physicist is thinking, "Oh no, this has too many unknowns. That's gotta be really hard. Think, there's gotta be a way to avoid doing all that work." And what backpropagation through time is, we can say that backpropagation through time is the blackboard full of formulas, so full of the intermediate states that have to be saved and stored in memory, and the recurrent backpropagation is just a simplification that performs fixed point iteration in the last two hidden states, and we don't have to go through all of the computational graph. Now, the second paper is stable and expressive recurrent CNNs. So this was authored by Linsley. It's a paper from the Thomas Serra lab, which is also the same lab of the computing a human-like reaction time metric. This paper goes on the premise that recurrent CNNs that are trained using recurrent backpropagation are hurt by the nature of this algorithm, because this algorithm optimizes the recurrent CNN in a steady state. And they say that optimizing the recurrent CNN in a steady state is bad because in the steady state we don't have all of the information that was needed to reach that point. So imagine that you have a hidden state that, let's say this is H, and that our matrix U is going to perform descent in some landscape of energy. You can think of energy models. I think it's a good example. And as you go down this slope, the derivative or the update function is going to get lower and lower. And I have like these blue to red color map representing the magnitude of the gradient. And when we are at this steady state right here, it's difficult to capture all of the useful information in order for the model to be expressive. And that the main information is encoded in these first iterations. But these first iterations are forgotten since we are only optimizing in the last two states. So they propose a Lipschitz coefficient penalty, which is basically the vector Jacobian product. And they try to regularize this function f such that it equals to a certain constant lambda. Now this lambda is the Lipschitz constant, and when this constant is less than 1, it means that we are learning a contraction map. When it's equal to 0, it's a really strong contraction map, and as it's closer to 1, we can get some expressivity while being stable, so while converging. So that's what the authors did. In their results, they compare the feed-forward version of the ResNet 50 with the version that implemented the contractive recurrent backpropagation algorithm that they are proposing with the Lipschitz coefficient penalty. And with the feed-forward version, with the same input, you always have one shot to get the output, right? So it's fixed. You don't have a dynamical system. And here we show examples of images where the belief map is wrong. So where there is a rock, the feed-forward is recognizing a ship with 67% likelihood. And here in this picture where, I don't know exactly what's in this picture right here, but it's recognizing a zebra where there is not a zebra. And they show that with the recurrent backpropagation algorithm, this belief is suppressed. They further show how the dynamics of their model work. So in the first few iterations, it starts by segmenting the middle parts of the objects. So for instance here, where there truly is a zebra, it starts by segmenting the middle part of the zebra and then propagates its belief to the outer parts. The same happens for the picture of the kids right here. Now, what's really interesting about this type of segmentation is that whenever you start in the middle, so the recurrent neural network that they are proposing starts in the middle and propagates the belief map to the outer parts of the body. And the same happens with the Voronoi flood field. So this is a set of polygons, and they first segment the middle polygon, and it starts spreading the belief to the neighbors. And somehow, this is related to the way that the human brain does segmentation. So there's a lot of brain science studies that claim that our visual system performs segmentation in this way. So this is basically a biologically plausible model for segmentation. Now to the main and I guess the star paper of this presentation, computing a human-like metric, reaction time. So let's go baby steps. This uses a gated recurrent unit with horizontal connections, meaning that the features or the pixels are connected to each other, to their neighbors. It also applies the Lipschitz coefficient penalty. So basically, we are using the recurrent backpropagation with the contraction map penalized by this regularization term that we just looked at. And it adds a new term, which is basically the evidential loss. Now, I'm not going to go into much details in this loss, but you can look at it in the following way. So the cross entropy is the same as taking the negative log likelihood of a multinomial distribution, and the evidential loss, specifically the loss of the risk right here in the middle, is equivalent to taking the negative log likelihood of a multinomial distribution with a Dirichlet prior. Dirichlet. So you have an error here with the ground truth. This term right here accounts for some variance, and they also penalize with the regularization, so that the concentration parameter of the Dirichlet distribution for the logits that are not the true targets is uniform and flattened. So in this paper they have multiple experiments. The main one is they have images of shapes. For instance, we see here horses, and they have two fixed points, and the goal is to check if these 2 points are inside the same object. And so they forward this to their model, which is the convolutional RNN. They performed fixed point iteration, so they iterate through it multiple times, and the output of this model is a set of alphas. So these alphas are the parameters of the Dirichlet distribution. And whenever these alphas are the same for both logits, so for the no and for the yes, the uncertainty is going to be high. And whenever this alpha is more concentrated to one side, so when one is a lot higher than the other, the uncertainty is going to be lower. You can think of the uncertainty metric as the entropy. And so what they have now is a system where they can evaluate the uncertainty at each time step that they evaluate their model. And they observe this phenomenon where the uncertainty increases in the beginning and then decreases in the end. They define a new metric, which is CRNN, which is basically the total uncertainty over time, which is the sum over all time steps. Now, one really cool thing that I'd like to talk about, and that is present in their results. So if you look here at the bottom part of the image, they have this fixed point right here, and then they compare results of other possible fixed points for the other candidates, right? And they label it with class D, A, C, B, and they measure the mean uncertainty of their model for each one of those sets of points. And they saw that it is lower for A, and as we go to B, C, and D, it increases the uncertainty, and the same phenomena is observed with human reaction times. So they had a set of humans, they asked them to answer if the 2 points are inside the same object, and the reaction time is correlated with the uncertainty measured. Here on the top, we have projected in the two principal components the trajectory of the logits yes or no for each pixel. So they see that they diverge in time, and this right here is the hidden activation map of the belief, right? So you see that basically propagates horizontally, so to the neighbor pixels, the point's belief. And this bottom part right here, I think it's better shown in these slides, where they also plotted the heat map that, given one fixed point, what is the uncertainty for all of the other possible points. And the closer it is to that fixed point, right, it's going to be a lower uncertainty, and as we get the second point further away, the uncertainty increases. And one thing that's also really interesting is that if we are inside the same object, and the path to that, from that fixed point to the other, is not convex, so if we have to do a curve, right, the uncertainty in those pixels is going to be higher. and outside of both objects the uncertainty is kind of low, and inside the other object the uncertainty is really high. A second test where they evaluated the model was, we have here a ball which is in cyan. I don't think you can see, it's where my mouse is. So we have basically a set of barriers, and the goal is to say where this ball is going to fall, if it falls in the left or in the right beam. So it's a binomial task again. So they tested these with humans and with their model, and they kind of see that there is a linear relation between the human reaction time and the size. On yet another task, we have a labyrinth where you have 2 points, 2 red dots, and the goal is to answer if there is a path that connects the 2 dots. Here in this test, they compare the uncertainty with the total path length, and it is highly correlated, right? So the relationship is linear between the 2 variables. And we can see here how the hidden activations work, and here the graphics over time of the uncertainty. I have a really cool demo to show afterwards that Halfer is made available. On the yet is another task. We have sets of images. The target is binomial as well, so it can either be natural, so we have sets of trees. Here we have a landscape, it's natural, and here we have a coliseum and sets of buildings which are basically man-made. And they have these metric right here of discriminability. I don't know how they got to this metric, but the message to take home is that the psi, so the uncertainty, as the discriminability increases, the uncertainty is going to decrease, and the same happens from the human reaction time. Now, this is the demo that I wanted to show. So basically we have the input. This is the maze example. The input of the neural network, and here the hidden activations. As you can see from the points, they start to propagate the activation throughout the path. And in the beginning it was predicting no, right? And with a high uncertainty that was increasing and increasing, and when the paths join, or a little bit after the paths join, the prediction is going to turn to yes, and then the uncertainty is going to lower. Yeah. So this is the main topic of this paper, is that it predicts human reaction times because they evaluated with humans. So I hope you like this video, and see you another time.